Hey, let me describe for you a typical laboratory exercise you might do to investigate the nature of the LRC series circuit. Okay, so some of the materials that we would use in the experiment are shown before you. Here's a circuit board. It's prefabricated by Pasco, one of the educational scientific companies that puts together materials. And it's a board that already has mounted on it a few elements. Now, I don't know how well you can see this. Let me pick a good color. How about orange? There's a resistor, and a resistor. So the board gives you a choice of 3 different resistors that you can use, but there's only one choice of inductor. There it is right there. I'll just say capital L for inductor. Put R over here for your choice of resistors. And then the circuit also provides you with a choice of 2 different capacitors. So you can customize the resonant frequency for this circuit. If you recall, resonant frequency is 1 over the square root of the product of inductance and capacitance. So by choosing different resistors, by choosing different capacitors, you can change the resonant frequency. And then choosing different resistors will allow you to change the maximum amount of current you can get in the circuit. So maximum amount of current is equal to the EMF divided by the impedance. And the impedance depends on resistance and reactance according to the following equation. So anyway, the circuit is customizable, but the way you hook it up is with these patch cords. Okay, so here it shows 1, 2, 3, basically 1 for the inductor, 1 for the resistor, and 1 for the capacitor. So you take a pair of banana leads and you take the red one and you plug it in. Let's say you choose the middle value resistor. So there's a red cable, and this is going to go off to a power supply. And then you take a black cable and you hook that up. Let's say you choose the larger of the 2 capacitors. And so these wires go off to the outputs of your power supply. And so if you follow this circuit, you can see there's only one pathway. The flow of current leads through the one chosen resistor, and then it spirals through the coils of the inductor, and then it leads to the one chosen capacitor. And so there it is. It's a series circuit. The inductor, resistor, and capacitor are all in series with one another. And then you measure the output voltage for each individual circuit element. So you take these patch cables and you take the red wire of one of them and the black wire of the other. And now it's typical to use red and black for DC, and you're going to power this off AC, but in this case you're just making sure that you're at any instant the polarities are going to agree. So you're going to combine instantaneous high potential with instantaneous high potential and low with low. Hopefully that makes sense. Okay, and then you need to put another one across the inductor. So a red cable here and a black cable here. So that goes off to measure. Let's draw this in a little better. That's going to go off to measure the voltage across the inductor. These 2 go off to measure the voltage across the resistor. And then you probably guessed it, take a red cable here, take a black cable across here, and then that goes off to the voltage for the capacitor. Okay, and so the way they plug into the voltmeters are with these ends, and the voltmeter actually is built in to a single unit, so it's this unit shown right here, which then feeds into a laptop computer, so you can view the voltages on your laptop all at once. So you get to see voltage across the resistor, the inductor, and the capacitor, and you can actually see them shown graphically. So you might have seen in a previous example problem that you can graph together the voltage across a resistor along with the voltage across an inductor along with the voltage across a capacitor all on one set of axes, and so that's what you get when you plug this interface unit into your laptop. So in the end, it ends up looking something like this. You got all these wires sticking out of the circuit. You have the cables put into the interface unit. You turn the whole thing on, and then you hit the settings, and next thing you know, on the screen of your laptop computer, you've turned it essentially into an oscilloscope, and you can see all of the output voltages. Now there are 4 of them, right? We've got 1, 2, 3, 4 different. There's a blue, there's a red, there's an orange, and there's a green. So the question is, can you identify which one is which? Which one of these graphs for voltage corresponds to the inductor, the capacitor, the resistor, or, of course, there's a complete output voltage here. Let's see if we take this wire, read up, this goes off to the power supply. That's the input. Yeah, all 4 of them are graphed simultaneously. In fact, here's our first question. The analysis of this lab, the data is just hitting run on the computer and collecting the data so you get this graph. The analysis comes from trying to interpret what the graph's telling you. Can you figure out from a graph like this what's the maximum voltage across the resistor? Well, every one of these curves labels the maximum value. The orange curve has a maximum value of 168 volts. Our red curve has a maximum value of 150, and so on. The green one, 125. The blue one has a max value of 50. So really the question is, can you tell which one of these curves corresponds to the resistor? So here's actually the way I would answer this one. I would say the resistor is the one that's not the inductor and not the capacitor. And I know this, that voltage across the inductor and voltage across the capacitor are always 180 degrees out of phase. So can you find the 2 curves on here that are 180 degrees out of phase? Yeah, you see it, don't you? The 2 curves that are 180 out of phase are this blue curve and the green curve. So those must represent inductor and capacitor. I haven't made up my mind exactly. Maybe you have figured out which one is which, but for now, let's not worry about it. We just know that the voltage across the resistor now has to be the red one or the orange one. But the larger of the 2 should be the overall voltage, right? We have an equation that tells us that the overall output voltage is equal to the square root of voltage across the resistor squared plus the difference between the voltage across the inductor and voltage across the capacitor. Well, that's a plus sign, right? And this value, unless driven at resonance, is going to be, well, something other than 0. So the overall output voltage has to be greater than, well, I guess I should say greater than or equal to. In the case of resonance, it would be equal to, but generally greater than the maximum voltage across the resistor. So now we know. Let's go in and label these. The orange one must be the total output voltage. The red curve must be the voltage across the resistor. Now, out of the blue and the green, which is the inductor and which is the capacitor? Well, Eli the Iceman gives us the answer. The voltage across an inductor leads the current, whereas the voltage across a capacitor comes after the current. Eli the Iceman. So if we look at the blue curve, we can see it reaches its peak a little bit earlier in time than when the voltage across the resistor reaches its peak. Whereas the voltage across the capacitor is reaching its peak value a little bit later in time. Early, what is leads, after, lags. So we figured it out. The blue one is the voltage across the inductor, and so the green one is the only one left. That must be voltage across the capacitor. So what's the maximum voltage across the resistor? We just have to read it off the graph. It's 150 volts. What's the driving frequency in hertz, and what's the driving frequency in radians per second? Well, frequency is cycles per second. So let's see how long it takes for a cycle. All of the voltages oscillate with the same frequency. So let's just pick any one and see if we can figure out a couple of time stamps. Now, I've made a mess of this, so I'm going to erase my labels. We can always come back and put it back in. Let's see. Oh, here we go. The only one that shows us two values of time is for the voltage across the capacitor. We're shown that the voltage across the capacitor reaches a peak value of 125 volts at time number 1 equal to 0.015 seconds. And then we're told again it returns a full cycle later to 125 volts at a second point in time, 0.025 seconds. Oh, well, if we know the difference in time, that stands for the period. The period is just time 2 minus time number 1, 0.025 seconds minus 0.015 seconds. So that gives us what? A period of 0.01 seconds. So it makes one cycle in that amount of time. Frequency is just the inverse of period, completing one cycle in 1/100th, in 1/100th of a second. So our frequency is 100 hertz. And angular frequency is always 2 pi times standard frequency. And so our angular frequency is equal to 628 radians per second. Not too bad. We were able to analyze and figure out our answers to 1 and 2. Let's move on. There's more investigation to be done in a lab like this. Can you figure out the phase angle? So phase angle, let me remind you in the form of a phasor diagram what phase angle represents. I'll try to be consistent with my color scheme. Voltage across the resistor. At some point in time, the phasor might point into this quadrant. Voltage across the inductor. Let's see, that was our blue one. Voltage across the capacitor, there's the green one. Now if I'm really drawing it to scale, this would be 125 volts. That's 50 volts. And this is 150 volts. Well, I can reduce that phasor diagram, keep the 150 volts across the resistor the same value. Don't change that phasor. There's my 150. That's my maximum voltage across the resistor. But I can combine the voltage across the capacitor and voltage across the inductor as one single vector. I might as well draw this, we'll just draw it in gray. What's 125 minus 50? Yeah, 75, right? 75, the angle between those is 90 degrees. We use the parallelogram method for vector addition, and we find an overall voltage. Now that one we know is, keep the labels consistent, that's our orange. So we have a total voltage here. So we can see there's an angle that exists between the voltage across the resistor, and by the way, let me use purple. I can draw another phasor like this. You know what phasor I just drew? Yeah, right, that's the current phasor, because current and voltage across a resistor are always in phase. And so we define phase angle as the phase relationship between the current and the EMF. And if the EMF lags behind the current, then we have a negative phase angle. So that's what we're asked for in this question 3. What is that phase angle? So we can see that the voltage across the resistor reaches its peak value at a moment in time. We'll call it T, how about A for lack of anything else? TA is equal to 0.0225 seconds. And then a little bit later in time, we'll call this T subscript B, that's when the voltage across the whole circuit reaches its maximum value of 168 volts, and that's at a time of 0.02324 seconds. Okay, so now keep in mind the period we found just a moment ago was 0.01, 1/100th of a second. So let's find something called delta T, the difference in time between the moment when the current reaches its peak value. And you say, wait a minute, current? I thought this was a graph of voltage across the resistor, not current. Yeah, but trust me, they're in phase with one another. So the current reaches its maximum value at time TA. The voltage across the whole circuit reaches its peak value at time TB. They're not perfectly in phase with each other. Their phasors do not line up. So delta T would be equal to 0.02324 minus 0.0225. Grab a calculator, let's see what that is. 0.02324 minus 0.0225 gives us a delta T equal to 0.00074. So let's make a ratio. The total period is to 360 degrees what this time difference is to our phase angle. So then we can just cross multiply. Say phase angle must be equal to 360 degrees multiplied by delta T over the full period. So our phase angle is 360 degrees times 0.00074 seconds divided by 0.01 seconds. Okay, grab the calculator again. And this comes out to 26.64 degrees as the phase angle. Now that's believable. If the distance from there to there represents 360 degrees, then the distance from here to here must represent 180 degrees. So it seems reasonable that the distance from here to here would represent about 26.6 degrees. Oh, careful. Did you catch my mistake? There, I fixed it. Negative 26.64 degrees. This is a circuit that's behaving capacitively. The voltage across the capacitor is greater than the voltage across the inductor. So the combination of their two voltages lags behind the current, and therefore our overall EMF lags the current. It's a negative phase angle. The resistance in the circuit is given as 300 ohms. What are the values of the inductance and the capacitance? Oh, well, there's a leap. How about this? We know the maximum voltage for the whole circuit is 168 volts. So let's see if we can figure out what the maximum current is equal to. Oh, and we also know the maximum voltage across the resistor is 150 volts. Actually, that's very useful, right? According to Ohm's law, the maximum voltage, capital V, across the resistor is equal to the maximum current, capital I, times the resistance. So this means our maximum current in the circuit is equal to 150 volts divided by 300 ohms. Well, there's some mental math for you. Our maximum current is half an amp. Okay. The maximum voltage across the inductor also follows from Ohm's law if we use reactance instead of resistance. In other words, if I multiply the maximum current times the inductive reactance, that gives me the max voltage across the inductor. So the inductive reactance is equal to the maximum voltage across the inductor divided by the maximum current in the circuit. So we just have to look at our graph, recognize that the blue curve represents voltage on the inductor, which has a maximum value of 50 volts. So 50 volts divided by 0.5 amps gives us a reactance of 100, right? 100 ohms of reactance. But we weren't asked about the inductive reactance. We were asked, what is the inductance? Well, the inductive reactance should be equal to the angular frequency multiplied by the inductance. So inductance is inductive reactance divided by angular frequency. So it's 100 ohms divided by 628 radians per second. So we get an inductance of about 0.16 henries, or if you want, we can say it's 160 millihenries. Now we need to find the capacitance. Well, again, something like Ohm's law. The maximum voltage across the capacitance is the maximum current multiplied, don't say resistance, call it reactance. If I multiply capacitive reactance times max current, I get max voltage on the capacitor. So this means our capacitive reactance is equal to the maximum voltage on the capacitor divided by the current. By reading our graph, we see the maximum voltage across the capacitor is 125 volts. So 125 volts divided by 0.5 amps gives us 250 ohms. And I also know that capacitive reactance is equal to 1 over omega times C. Now what's that mean? A little cross multiplying here. And capacitance is then equal to 1 over omega times capacitive reactance. So our capacitance is equal to 1 divided by 628 times 250. And we have a capacitance of 6.37 times 10 to the negative 6. Or if you prefer, 6.37 microfarads. 160 millihenries, 6.37 microfarads. Well, that took a little work, but we were able to figure it out. What's the current amplitude? Well, we already figured that out along the way. The current amplitude, that's the maximum current, right? That's equal to half an amp. So what's the RMS current? An RMS value is always equal to 1 over rad 2 times the max value. So 1 over rad 2 times 0.5 gives us 0.354 amps, or if you want, instead of 500 milliamps, 354 milliamps. What's the capacitive reactance, inductive reactance, and impedance? Well, we already found the capacitive reactance. That's 250 ohms. We found the inductive reactance. That's 100 ohms. So let's find the impedance. The impedance is equal to the square root of the resistance squared plus the difference between the inductive reactance and the capacitive reactance quantity squared. So this gives us the square root of, weren't we told that the resistance is 300 ohms? So we've got that value. So the square root of 300 squared plus 100 minus 250 quantity squared. So we get an impedance of 335.4 ohms. Let's see. Check to see that the relative values of reactance agree. Let's check something out here. Our maximum voltage for the whole circuit is 168 volts. Okay, so let's see, is this right? Maximum current or current amplitude should be equal to max EMF divided by impedance. So 168 divided by 335.4 gives, lo and behold, 0.5 amps, exactly what we'd expect. So yes, everything seems to agree. That's a long example problem, but hopefully it gives you even more insight into the behavior of these RLC circuits. If you ever have a chance, I recommend you complete this lab. Seeing the examples worked out is one thing, but collecting the data yourself is quite another. Thanks for watching. Stay tuned for more.